Somewhere beneath the frozen surface of one of Jupiter's moons, there is very likely an ocean containing more liquid water than every ocean on Earth combined. Scientists have suspected this for decades. The evidence keeps getting stronger, and yet, if you asked the world's leading planetary scientists exactly how humanity is going to reach that ocean and check it for life, you would get several completely different answers from several competing teams, none of whom are entirely sure their approach will actually work. This is the strange position we're in. With Europa, we are more confident than ever that the conditions for life might exist there. We are far less confident that we currently possess the technology to go find out. Let's start with why Europa matters so much in the first place. It's one of Jupiter's 4 large Galilean moons, roughly the size of Earth's own moon, and its surface is a shell of solid ice, crisscrossed with long reddish-brown cracks that give it an almost cracked eggshell appearance. Beneath that shell, based on magnetic field data and surface geology gathered across multiple missions, scientists are confident there's a global ocean of liquid salt water kept from freezing solid by heat generated through tidal flexing as Jupiter's immense gravity squeezes and stretches the moon with every orbit. Unlike Mars, where any search for life is a hunt for microscopic fossils in ancient, long dry rock, Europa offers something rarer, the possibility of present-tense biology. Liquid water existing right now, potentially in contact with a rocky seafloor that could supply the chemical ingredients life as we know it requires. If Europa's ocean is habitable, whatever might be swimming in it wouldn't be a relic. It would be happening. NASA's Europa Clipper mission is already on its way there, launched in October of 2024, and expected to arrive in the Jupiter system in 2030. When it does, it will conduct dozens of close flybys, mapping the ice shell, sampling the thin atmosphere, and gathering the most detailed data we've ever had on whether that ocean could actually support life. But here's the part that surprises a lot of people. Europa Clipper isn't going to land. It's not carrying a drill, a submarine, or any instrument capable of actually touching that ocean. Its job is reconnaissance, confirming whether the conditions are right, and figuring out where a future mission might safely try to go deeper. The actual search for life, if it ever happens, is going to require an entirely separate mission, one that doesn't exist yet, because the technology it depends on hasn't been finalized. That technology needs to survive an environment that is, by any measure, brutal. Jupiter's magnetic field is the largest structure in the solar system, and it whips charged particles into a storm of radiation intense enough to fry ordinary electrons and, in the words of one autonomous systems researcher at Woods Hole Oceanographic Institution, enough to kill a regular person within a few seconds. Any lander attempting to survive on Europa's surface long enough to do useful work needs serious radiation shielding just to function. Then there's the ice itself. Current estimates put Europa's ice shell somewhere between 10 and 18 miles thick, more than twice the height of Mount Everest, stacked straight down. Something has to get through all of that before any search for life can even begin. This is where the real disagreement starts. Not disagreement about whether Europa is worth exploring. Everyone agrees on that. But genuine unresolved disagreement about how you actually build something capable of getting through that much ice, reaching the ocean, and reporting back what it finds. The most straightforward concept is called a cryobot, essentially a melt probe that uses heat to gradually thaw its way downward, pulled by gravity, rather than mechanically drilled. NASA has developed a concept called PRIME, short for Probe Using Radioisotopes for Icy Moons Exploration, which would generate that heat using the decay of a radioactive element like plutonium-238. It's elegant, in a sense. Know the thickness of the ice, and you know exactly how much radioactive material you need to bring. But using nuclear material to punch through the ice shell raises an immediate follow-up problem. How do you make absolutely certain that radioactive matter never reaches the ocean itself, contaminating the very environment you're trying to study with Earth-based radioactive material, or with any Earth-based biological material for that matter, would be a catastrophic scientific and ethical failure. NASA and other agencies take planetary protection protocols extremely seriously for exactly this reason, and a self-powered nuclear probe raises real, unresolved engineering questions about containment. Partly because of concerns like that, other teams are pursuing entirely different approaches. JPL's Ocean Worlds Reconnaissance and Characterization of Astrobiological Analogues project, known as ORCAA, is testing a cryobot that skips the nuclear question entirely. It's electrically heated instead, with power delivered through a tether connected to a surface station. In field tests planned for Alaska's Juneau ice field, an 8-foot cryobot was set to attempt melting through 1,000 feet of glacial ice, aiming to reach an ancient subglacial lake. A separate international effort, the Technologies for Rapid Ice Penetration and Subglacial Lake Exploration Project, or TRIPLE, led by researchers at Germany's Center for Marine Environmental Sciences, is developing a similar electrically heated cryobot, but this one is designed to deploy something extra once it reaches liquid water. A tiny autonomous underwater vehicle, just 20 inches long and 4 inches wide. It can detach, explore, collect a water sample, and dock back with the main probe to recharge the team planned to test this entire system on the Antarctic ice shelf near Germany's Neumayer 3 research station in the spring of 2026, deliberately choosing one of the most Europa-like environments Earth has to offer. Then there's Stone Aerospace's VALKYRIE, which takes a completely different route to generating heat. Rather than electricity delivered through a tether or radioactive decay, VALKYRIE uses a high-powered laser transmitted down through a fiber optic cable to melt the ice ahead of it. It's an approach designed specifically to avoid both the nuclear contamination problem and the practical limits of how much power a tether can realistically carry over miles of cable. And JPL has also been developing something that looks nothing like any of these, a robotic snake, part of a project called the Exobiology Extant Life Surveyor, or EELS, designed to wriggle and crawl its way through crevasses and vents rather than melting a straight vertical shaft. It's already been field tested navigating the icy terrain of the Athabasca Glacier in Alberta, Canada. built with an eye less toward Europa specifically, and more toward Saturn's icy moon, Enceladus, where active geysers might offer a shortcut into the subsurface ocean without needing to melt through miles of ice at all. 4 fundamentally different engineering philosophies. Radioisotope heating, electrically tethered melting, laser-powered melting, a crawling robot that avoids straight-line drilling entirely, each with real prototypes, real field tests, and real institutional backing. None of them yet proven at anything close to Europa's actual scale. And even solving the descent doesn't solve everything. Once a probe reaches the ocean, it needs to maintain a communication link stretching back up through miles of ice to a surface station, and from there, across roughly 600 million kilometers of space, back to Earth. Losing that link at the critical moment would be, in the words of one JPL research scientist, close to the worst possible outcome imaginable. What would be worse than finally finding life somewhere else and not being able to tell anyone about it? If a probe melts a clean shaft downward, and that shaft isn't somehow sealed behind it, the pressure difference between the ocean depths and the near vacuum above could cause a blowout comparable to an uncontrolled oil well eruption, potentially launching debris or the probe itself back up through the hole it just spent years digging. And Europa's ice isn't necessarily stable. While all this is happening, thanks to the same tidal flexing that keeps the ocean liquid, the surface is geologically active, prone to fracturing, shifting, and occasionally erupting. A multi-year descent has to account for the possibility that the ice around it won't stay put the entire time. Taken together, this is why serious researchers describe the challenge less as a single hard problem, and more as a tightly stacked chain of separate hard problems, any one of which could end a mission on its own. Survive the radiation, melt or drill through up to 18 miles of shifting ice, avoid contaminating the ocean, maintain communication the entire way down and back, avoid a catastrophic pressure blowout, and only then actually begin the scientific search for life. None of this means the mission is impossible. If anything, the sheer number of independent teams at NASA, at multiple universities, and at private aerospace companies, all racing to solve different pieces of this puzzle in parallel, suggests real confidence that it's solvable eventually. But it also means the honest answer to how do we check if there's life on Europa isn't a single, confident plan. It's several competing, partially tested approaches, each betting that their particular solution to the ice, the power, the pressure, and the distance will be the one that actually works when it matters. Europa Clipper won't answer this question. It will only sharpen it by telling us more precisely what that ocean is actually like and exactly how thick a shell of ice future engineers will need to get through to reach it. For now, the ocean sits exactly where it's been for billions of years, patient in a way nothing on the surface has to be. The real race isn't really about reaching Europa anymore. We're already headed there. The real race is figuring out, before we arrive, which of these very different machines will actually be capable of finishing the journey once we do. Beyond what you can see, but never beyond what you can understand. Subscribe and check out the rest of the channel. New episodes on space, physics, and the edges of what we understand, with new content going up every day.